Again, so we're looking at a cell membrane, neuron axon membrane with its leaky sodium and potassium channels and the sodium potassium ATPase thingies up here at the top. And so what this gives us is what you end up having is sodium wants to leak out. And so basically you will have three positively charged sodium ions. They want to leak out. And then you have two potassiums that want to leak in. And what this does is it gets the inside of the cell at somewhere between 0 to, or it goes from 0 millivolts in this process to -5 millivolts. Now you're asking yourself, how in the world does a bunch of positive ions going in and out of a cell give me negative voltage? And this is understandably difficult thing to think about, but this is why when we started electricity this semester, we were talking about those spheres, and if we induced a charge separation with a plus or minus stick coming in from the side, how would we polarize or depolarize that object? And so here there is polarization by virtue of a gradient, and there's two kinds of gradients that get talked about in this game. And most, if not all of you, you'll either take a course dedicated exclusively to membranes and mostly about what we're talking about today, except you'll go for, a semester length at it, or the course will be majorly about this. And you will have similar biophysics kind of math and ideas to keep track of. This is how drugs work. This is how the muscles move. Cognition happens. Every cell goes through this process and has these sort of things. And by the way, I've only listed 3 of dozens of channels that are on cells, and I'm listing the 3 most significant ones, the main event, if you will. But there are more, and we'll talk about that as we go. So it's slightly negative on the inside because there's more positive on the outside. Okay, so this makes inside of the cell slightly negative. That's what those sodium potassium ATPases do. And there's this exchange here. And after we go through this, we'll kind of look at there's a simulation, I've shown it to you before, an axon being stimulated towards action potential. And that will make more sense after we get into the nitty gritty. So there's that piece of the puzzle. Now, what happens next is you have these leaky sodium channels. And so just like it says, what you're going to see is these sodium coming in. To these channels. Now, these leak less than the potassium. All right. There's more potassium channels, and they let more potassium go out. But what the leaking in of a little bit of sodium, okay, is what tends to drive the inside of the cell down to a -70 millivolts. All right. And that's the resting membrane potential, which gets not substituted, it gets acronymed, gosh, I need more coffee, as RMP, so resting membrane potential. So there's a voltage across that membrane. So every cell in your body right now is going through this process as we speak. If you moved, if you thought, if your stomach gurgled, yeah, there was this going on. Yeah, there you go. There was just a whole bunch of action potential that led to this, me flipping my arm around or whatever, turning, talking, thinking, all that jazz. So this is just going nuts inside of all of us right now, going through from a resting potential. There's an activation that gets all of these things flowing, okay? And then there's these leaky potassium channels. And so there's way more of them. That's why I put more of them on the picture. Okay, so all this potassium leaking out of the cell. And all of this, this drives it further down to a minus 90 millivolts inside the cell. And so there's this polarization of the cell. So we talked all the dry, boring, bland physics of electricity stuff that we've spent most of the semester on, getting into circuits now, and circling back now that we have a lot of experience and thoughts and some knowledge about electricity, voltage, which is a more complicated idea than just stuff moving. It's why stuff moves. And so voltage here inside of our bodies, it's why stuff moves. It's why stuff changes in our mind, in our body, and you name it. All right. And so if some of you go into pharmacology, you're going to know this stuff inside it. You'll be the people who will certainly have a full semester-length course on just membrane stuff. And it'll be largely about how this works and what influences it, how drugs interact with it, why this drug, why do some people need extra potassium? Well, because they have too much sodium. So you can see if your sodium potassium levels are whacked, then your cell function's whacked. All cell functions. So that will damage your vascular system, everything. It's so simple from a kind of physics, biochemistry perspective, relatively simple, but what a huge impact. All right, so that is the sort of the basic just setup here. And so some facts to put in with this is these leaky channels, they're always open. That's why they're called leaky, okay? Both leaky channels are always open. There's some stuff in here. Normally, the potassium, sodium, and whatnot, they're cations because they're positive, and they're normally bound to some sort of anion, a negative, okay? And phosphates and proteins, okay? So and other things, but I'm trying to I always forget how to spell proteins. It's probably wrong. It's one of those words where you're like, did I do that right? I before E except after C, or when followed by Y, or sounding like A as in neighbor or way, or on weekends and holidays, and all through the month of May, because you'll always be wrong no matter what you say. I hope that's right. Proteins. I'm just going to say that that's the way you spell proteins, even if it's not. And so normally they're bound to that, but those things don't get transported out when these leaky cells. So there's a gradient. And I mentioned earlier there's two kinds of gradients. There's a concentration gradient, and so put on your chemistry hat and think concentrations. If you have more of something on the inside than the outside, then which way does it want to flow? It wants to flow downhill, so to speak. And if you have less of something on the inside and more on the out, then it will want to flow downhill. So you got two downhills, an in and an out downhill. Okay, so there's a concentration gradient, and that concentration gradient has its own electrical gradient called a voltage difference, a difference in electric potential. Okay, so that's the connection between this biology, this physiology thing, and the physics and the chemistry. And so in many ways, I sort of like this version of physics for the life sciences a little bit more than the other one, because of we get to swerve into these kinds of applications, and it's spot on with the stuff you need to know in the future. Obviously, they still need to know it in the other class, but the direction towards engineering is just a different direction of things, and we have different goals, at least a little bit. So anyways, here's this stuff. Some other facts here. All of these leaky things they're there to polarize the cell. So every bit of this is about making the cell on its inside more negative. And something else has to happen to depolarize that. That's what the action, this process that goes through the opening and shutting of all these different channels. There's a action potential that gets this polarization going, and then it hits a peak and depolarizes as they start to shut down. That's the simple. Now, why is it that potassium's more leaky? Well, one short answer is because the cell membrane is simply more permeable to potassium. And so this is based on a lot of things: how many channels there are, the way those channels work, the shape of those channels. But it's just the bottom line is the cell membrane is more permeable to potassium than it is to sodium, way more permeable. Okay, and so potassium's always sort of winning. But if you're low on potassium, guess what your cell can't do? It's not going to win, and that's going to lead to cell damage, and cell damage is bad for you. In fact, we'll end this little lecture part with a discussion about that. No, I'm sorry, I was thinking of my textbook. I was writing in it yesterday. All right, so that's sort of one way to look at it. There's a couple other things there's a couple other channels that I want to talk about that are substantial to this. But just to be aware, there is a thing called a Nernst, for some person named Nernst, potential. And normally you don't hear about this at this level, but why not? This is a direct application of electric potential. They're essentially, we're about to talk about capacitors and stuff like that. But there's an equation, and it says the voltage that we're talking about here is going to be RT over ZF natural log of a concentration ratio. That's the formal thing. So R and T are the same R and T that you would see in the ideal gas law. Rydberg constant and absolute temperature. The Z is the number of, it's its ion number basically. And the F is a Faraday constant. And it's a Michael Faraday, yeah, that Faraday. And it basically, what was the Faraday constant? Did I write that down? It's basically the charge, the number of moles associated with the charge. It's basically just a molar extension of the fundamental charge constant. That would be a way to put it. And what it really works out, in practically speaking, the way that that's just the formal version of it. But typically I'm going to use the letter E, because that's a letter we use for voltage or the electric potential difference, what tends to happen is we would just go with 61.5 over this Z number, which in this case is 1. Where's the 61.5 come? There's a range of values from about 58 to 62 that are associated with the temperature. So it's that RT. So in normal conditions, this works out to be, it's 61.5 over your Z number. And then you're going to have this natural log of the outside concentration and the inside concentration. So that's what this right here, this is outside, inside concentration. And so that will vary in a number of ways, but typically, and it could be natural log or just regular log because the ratios, it doesn't matter. And in this case, you would have a concentration of, this would be typical of 5 to 150. And this is what gives you, this works out to be the minus 90 millivolts. Okay, so that's just kind of a quick, Nernst potential is something that you would see. I don't think it would take you, I don't think you'd have to wait till med school, biochemistry and specialized courses, but you'd see it again in med school as students see this. So there is some math to it. We are not going to develop or use that equation. This is about us using the thoughts that we have about electricity from the standpoint of classical physics, and we're going to apply it to a life science thing because that's what you guys and gals are here to get your life onto, a life science thing. All right, so that's a basic introduction to it. Now, all right, I'm going to clear that out and do another simple drawing here. So those were leaky channels. They're always leaking, and they will leak in accordance with concentration gradients, and they're more impacted by electricity, a voltage gradient, than the concentration, but both of those are always operative. All right, so now I want to talk about voltage-gated channels because these are the kinds of channels that are the main event, if you will, for an action potential. All right, and so these are going to be what are called ion-gated channels. So let's talk about this. And so there's or they call them ligands, ligand-gated ion channels. And so what does that mean? So for one, you could have a glutamate or you could have GABA. These are proteins that are a big deal. A lot of GABA going on in your brain. That out of whack will mess up those functions. And glutamate, I'm spacing on what that is. And so here's what is happening with, say, a glutamate channel. There's two things are going to happen. And again, we're back with the cell membrane. You're going to have sodium and calcium leak in. Now, beware that there are sodium and potassium channels, be they leaky or voltage-gated channels. There's calcium leaky channels, phosphorus, chloride, like pretty much all the salts that are in your body. There's one or more channels, leaky or voltage-gated ion channels, for them to go in and out of the cell. And we're not going to go through all of them. That was what you do in a course that's all about this. You would get into every nitty-gritty and work out all that balance, all right? Whereas the GABA is a different exchange. In fact, it's chloride coming in, which is negative, and potassium going out. So these are things that they are operated, again, by, there's a voltage. So it's not just a leaky, always on kind of thing. Voltage gets these things going, so these are depolarizing kinds of things. So there's got to be something that resets the cell back to its original state during this process. And so going back to the glutamate ion channel, this takes a 70 millivolt resting membrane potential. Textbooks tend to say minus 70 to minus 90, but generally speaking, in fact, there's been some direct measurements that verify this. And this channel will take us from the minus 70 to a minus 55, which is a threshold potential. This is where things can begin to happen. And this is called an EPSP, which is an excitatory, we don't use that word much, postsynaptic potential. So I know that usually people have had a biology course where you talked about this as well. And so there's the other thing, there's more connections to the other science courses you take, a few more in this course than the other one. And so I like doing that. You should be able to make connections all the way through your education. You shouldn't have to wait. It's sometimes you have to wait because you just need that knowledge and experience, but not all the time. And so that's an excitatory postsynaptic potential. So meaning it causes, it lets something loose. Whereas this GABA thing is the opposite. That takes us from a minus 70 millivolts to that minus 90 millivolts. And this is called an IPSP, and it's I for inhibitory. Inhibitory postsynaptic potential. So these are two other, and again, these are just two of a bunch more. There's all sorts of this and that, glutamate, this amate, that amate, GABA 1, 2, 3. There's all sorts of stuff, and so this isn't a biochemistry course, but there's physics there too. All right, so this is sort of the two big pieces of the puzzle that we are dealing with. I suppose I could have made a bigger square and done it all at once, but this gets busy really fast. And so there is a we'll see this when we run the simulation, but on a time scale, we're dealing with milliseconds. For voltage, we're dealing with millivolts. And what you have here, if we have the our resting membrane potential, which is at minus 70 millivolts, so 70 1/1000th of a volt, a very tiny amount of voltage. We have this threshold potential at minus 55 millivolts, and this threshold is what it means. It triggers an action potential. So if you might have all sorts of little bumps, and then if it hits here, then it's going to peak, and come around like this, and we'll see this in a minute. So this is, the graphs, people, this would be similar to stuff you'd see like in cardiograms and whatnot, but not exactly the same thing, but close enough. And so when you hit that threshold potential, that triggers the action potential, which is something we'll see here when we run the simulation. So what do we have? We have 5 main things that we've talked about that change, that polarize the cell and or polarize it or depolarize it. Polarizing effects from sodium and potassium channels and the sodium-potassium ATPases, and then depolarizing voltage-gated channels like these two here. And this lets us kind of zap it, and then it relaxes, and that you can rinse and repeat as your nervous system does whatever your nervous system does. Again, oversimplify. So those two clock diagram things, let's look at it in a way that's a little bit more real to life. We're going to actually get close to kind of an axon thing. So let's kind of try to put this together a little bit better. I'm going to put some sodium channels up there and some potassium channels down here. So this long part of the this picture is the axon itself. Up here at the far left, you have what's called the axon hillock. Weird name. I guess it's the back end. And then over here, on the other end, you have your axon terminal. And I think there's a synapse that would be out here somewhere that it's going to send some neurotransmitters to once all this. So we're going to go from a resting membrane potential to a threshold potential to an axon potential that causes the production of some neurotransmitters, and then those neurotransmitters go on to synapses or whatever and do their thing. All right, so that resting membrane potential goes to threshold potential, and so we go from a minus 70 millivolts to a minus 55 millivolts, and that gets this ship rolling. And so what happens is these gates start doing their thing, all right, and things get more positive on the inside, all right, and then there's some potassium that's going out, all right, and so what happens here is these things are it's a kind of it's stepping along. So we're having this polarizing wave or depolarizing wave as these gates, this first one opens, starts to make it more positive. That positive causes the other one to open, which makes it more positive, and so there's this, as you go down the axon, and so this is for a long axon. It would look like, I don't know, a little sausage all linked together, these little myelin sheathed chunks of the axon, and that signal goes down to the axon, and you have some let's see here, you have some voltage gated let me get a different color here. Oops, didn't want that. I am looking for, oh my god. So here we're going to have a calcium channel, so voltage gated calcium calcium channel, that's also going to get this more plus. And what's on the inside here? So what you have here are these little pockets, and what's going to happen here as this end of the axon terminal gets more positive, all right? In fact, this happens 30 millivolts, then these little things end up being pushed out of the end here, these neurotransmitters, okay? Okay, and then that goes on to do all sorts of stuff in your nervous system. Some simple ones, for instance, your circadian and ultradian rhythm. So your circadian rhythm is a 24-hour kind of thing, and your ultradian rhythm is a like an every 90 minutes kind of thing. So one of the key things for your circadian rhythm, so that you have proper sleep, there's a number of things that impact your sleep, is seeing sunlight at the beginning and end of the day. And so all you have to do, because there's one input to that center of the brain, which, if memory serves me, is, you know, in the bottom back here. I'm pretty sure it's there. There's one input to that circadian rhythm section of the brain, and it's through your eyeball. One ocular input. And if you don't have just under a minute of morning light and evening light to that ocular input to your circadian rhythm, then that rhythm will be off. And that if that rhythm's off, it's one of many things that will just tank your sleep. So what do? You want unfiltered light. So you don't need to go out and look at the sun. You just need to go out and see reflected light. So you could go stand on your patio and look at the wall, or go outside and look at a bush. If it's light out, you're getting that light. It's okay if you have glasses, because those don't filter, they focus. But the glass, like looking out a window, it would take an hour for that amount of light to get, because it's a particular wavelength. If memory serves me well, and I don't remember what that wavelength is. It's not just all the light, it's a particular wavelength. And so if it comes through glass, it's going to get we're going to be talking about that shortly, in a week or two, about how light moves through materials. So you want unfiltered light, no windows looking through, and you don't have to look at the sun. You want to do that in the morning and the evening, a minute, okay? And so and that's one easy thing. That input would be a stimulus that would eventually get you to an action potential that releases neurotransmitters so that the circadian rhythm does its thing. All right, so that's one way, or one application of this. And there's some really great, if you go to YouTube and just search neuron action potential, you will see dozens of videos saying exactly the same thing. There's one fellow who's particularly good, and he's a doctor somewhere, young guy, can't think of his name. But then there's a bunch of great animations of this, and so you have animations that are awesome, and then you have some lectures that go into all this detail and more out there on the web. So you can also get it right out of a textbook. That's where I got most of this, or a good chunk of it. And so what you have is depolarizing makes cell positive, repolarizing, gets back to resting membrane potential, or more, it makes it negative. And there's hyperpolarization, which makes cell more negative. All right, so these are the things, and you have to go through all three, and it's just rinse and repeat kind of thing. That's about all cell action, nervous system function, muscle action, et cetera, et cetera. All right. So I'm going to draw this graph one more time, but I'm going to get a bit more detailed and take up the whole screen. So time in milliseconds, voltage in millivolts. And let's put some important numbers on here. Minus 90 millivolts, minus 70 millivolts. You're thinking, wait a minute, that has to go below the axis. No, it doesn't. This ain't math class. We do whatever the heck we want, sort of. All right. All right, so we just want to, it's just a cleaner graph if we don't have to bother with all that. So here you have your resting membrane potential. Here you have your threshold potential. That's what gets an action potential going. And so you could be at this resting membrane potential with all sorts of things causing all this, and then poof, it jumps up super fast, and then will kind of do this sort of thing, and it'll fall and come back up. So what's happening in these ranges here? So let's do this. Right in here, this is a sodium rush. Get my colors right here. So this, I'll just call it a sodium rush. They don't do that in the textbooks, but this poof, this spike comes from this whoosh, a bunch of sodium coming in to the cell. So doing that is a depolarizing kind of thing. And then down here in this region, we have the leaky channels. Doing their thing, all right? And what it does is it sort of shuts down that runaway, because it would just kind of keep going. So those leaky channels shut down what would otherwise just be a kind of a runaway thing that would really whack the cell. So those are the big ideas. And a graphical representation. So your cells are going through this, ziggity zag all the time. And you might have a cell that spends an inordinate amount of time over here in this region where, it just, nothing's getting it to that threshold potential. So that you get a firing and you go through this depolarization process. But all this stuff works to keep this, so you have concentration gradients, which is a chemistry. Almost think of it as a fluid pressure kind of thing, but think of diffusion and all that jazz. And then you have electrical gradients. And the right way to think about all of them is as a hill. You can have a concentration gradient where things want to flow from a higher to lower concentration, physical concentration. And then you have your electric potential gradient, which we're talking about with circuits and whatnot, where you have a voltage hill, if you will. And different charged particles will go up or down that hill in accordance with that interaction. All right, so that is all I want to say about action potentials in terms of, I guess, the physiology of it. And what I want to do is in this lecture, before we move on to the next thing, with an example. So if we have an axon and then it has like this kind of key thing at the end of it. Like it's like a receptor down here. And so this is the membrane. We'll talk about. And it's the axon itself. So you have the helic end, or the cell, and then that terminal end down here, where the neurotransmitters and all that jazz goes off. So let's give this axon some data, some physics data, and we're going to relate this to capacitance, because axons have a capacitance. So we've talked about capacitors, talked about circuits. We're going to be putting those capacitors into circuits soon. And so the axon, the length of the axon is going to be 8 centimeters. The radius of it is going to be 8 micrometers, 8 millionths of a meter. Okay. The membrane thickness we'll call that D, is going to be really small, 10 to the minus 8 meters. And then it has a dielectric, not dielectric, dielectric, spelled like dye, D-I-E, electric, dielectric constant of 2.6. So every material that we would jam into a capacitor, because we almost never use air capacitors, increases the capacitance without having an actual charge transfer. All right, so here are some basic quantitative facts about, and these are typical values for the membrane. So we could, okay, what is the axon capacitance? Well, we have a formula for capacitance when you're dealing with something with these properties. And so you have this dielectric constant, which is a material property. And so a phospholipid bilayer, which is what all membranes are fundamentally. We have the permittivity of free space constant that we haven't used much because it gets bottled up in the Coulomb constant, which we also label as a K. So the symbol of use is epic in physics, as it is across all science. And so we can just plug and chug, because 2.6 was given as the dielectric constant. We could go look up the permittivity of free space. I think it's newtons per coulombs per newton meter squared. Yeah. And the area, okay, just going to be or the cross-sectional area ends up being 2 pi, and then we're going to be multiplying the 8 micrometers and the 0.808 meter length, and then this 10 to the minus 8 meters. And so you get a capacitance of 1 times 10 to the minus 8 farads, which would just be 1 nanofarad. And so seen a little bit of farads for Faraday with capacitance. So you have that. Then what about how much charge is moved? Well, delta V, or the voltage, okay, we have a change in voltage. That's what we know, that moves stuff. And it goes from, and I'll just tell you, it goes from a minus, in this case, we're just going to pick a typical value, from 35 millivolts, or it ends with 35 millivolts, starting from that resting membrane potential, which means you have 105 millivolts for the overall change in voltage in this process. And we know that delta Q, this is just from textbook stuff, is just C delta V, capacitance times delta V. So if we multiply our last number times this new number, we're going to get roughly 1 times 10 to the 9th coulombs. So 1 billion coulombs. That's a lot of coulombs. All right. And then C, we could find the number of ions flowing through this action potential. And that's just going to be the change in charge and fundamental charge constant, because each ion will have that electron ion. So think of your chemistry. And again, this will be 6.6 times 10 to the 9th ions. So we're talking about billions of ions in one cell. One cell. All right. So there you have it. You have a physiology overview, if you will, biochemistry viewpoint tied in with our physics for how all this electricity stuff applies to the life sciences. So this would be a major feature that would extend to everything in the life sciences, because this is why critters have cognition and muscle action. It's this right here. And again, everything I showed you today could be a whole course. You just go at this for weeks and weeks. So I'll leave it there for now.